Welcome back to the third video on Minkowski summation. My name is Ari Berestianu, and I'm going to focus today, talking about segments. Okay, so segment is a convex compact set which is bordered by 2 points. So let's start with R, and where things are relatively simple. A segment is just a line between 2 points, okay, A and B. Okay, that will be a segment. The only thing that we will ask, and we will talk about closed segments, closed sets, is that B is weakly, at least, bigger than A. Okay? So what is the sum of 2 segments, A and B, that and B and C and D, and what do we get out of Minkowski summation? So if I sum A and B, the segments A and B, Minkowski sum C and D, and again, C and D are such that these are weakly bigger than C, then the solution is very simple, or the segment that we'll get is, again, it's going to be another segment, and the lower bound will be A plus C, the usual summation in R, and the upper bound is B plus D. Okay, and that's the rule. It doesn't matter what A and B are, and C and D can be positive, negative, and any mix of them. The true thing here in R is that the length of the first segment, if I have segment 1, okay, for example, A and B, plus the length of the second segment, okay, will be equal to the length of the Minkowski sum of the 2 segments. Okay? That's it. It's very simple in R. Let's move to R2. Okay? Segments in R2. So now we will have 2 endpoints again, and the 2 endpoints can be any points in R2. Okay? So we have, let's say, P0 and P1, 2 points, 2 vectors in R2, like that. And what is the segment that connects P0 and P1? Okay, so I'm going to define U to be P1 minus P0. Okay, basically the length that will be, that segment will be. Okay, and the segment P0, P1 will be defined as all the points X in R2 such that X is equal to P0 plus T time U, and T is in 0, 1. Okay? And that's the segment. Okay, now the question is, of course, suppose I have 2 segments, and again, this is something that in partial identification we'll have to do. We will sum some segments. And what if I take 2 segments, the way I define them here? So I have P0, P1, the first segment, and I want to do a Minkowski sum to the another segment, Q0, Q1. Okay? Again, Q0, Q1 are start and end at 2 other points, Q0 and Q1. Now there are going to be 2 cases, 2 possibilities. Okay, so we will define, as before, U equal to P1 minus P0, okay? And we'll call V to be Q1 minus Q0, okay? And case 1 that can happen is that U and V are collinear. They are on the same line, collinear. Okay? If that's the case, then what we will get is another segment on the same line. Okay, so what will result from this case is that the sum, okay, the sum is a segment. And again, it's going to be a longer segment, but a segment. Okay. Case 2, okay, so that was the first case. Case 2, okay, U and V are not collinear. Okay. we'll draw a picture in a minute. Then the sum, okay, the sum is a parallelogram. Parallelogram, like that. Okay, so here is a picture. And then I'll draw a picture of case 2. So if we have R2, okay, and I have two segments, let's say this is P0, P1, like that, and I have another segment which is of a, it's not, they are not collinear, so it will have to be of a different slope, okay? So suppose the other one is this, okay? There are two segments, okay? So what, it looks like it's perpendicular, so let's try to change it. It's not perpendicular. It's another angle that is not related to the angle of the first segment. Okay, so what will result, the sum of these two, and I'll draw it on a different set of axes, okay, will be a parallelogram with two sides which are parallel to this, okay, this line. So two parts like that, where they are connected by sides which are parallel to this. So there it will look something like this. Okay, and again, that's just a picture, but it will be a parallelogram that looks like this. Okay, so if we think about now, we talked about lengths of segments. What is the area of P0, P1 plus Q0, Q1? So the area, okay, of the parallelogram, okay, the sum P0, P1 plus, oops, let's close this, plus Q0, Q1, okay, and that's Minkowski summation. And that will be the absolute value of the determinant. And in the, we'll take the determinant of the following matrix. We'll take the U and V vectors. We'll put U1, U2, V1, V2. Take the determinant, absolute value of it, and you can do the calculation. That's the area of this parallelogram. Okay? So that's the summation of segments in R and R2. If you have more than two segments that you are summing, in R it's simple. It's just the sum of the lower bounds and the sum of the upper bounds, and that's it. In R2, okay, the result of summing some n segments in R2 will give you a zonotope. Okay, a zonotope, okay, is a polyhedron in R2 and a polygon in R2, and it is going to have at most 2n vertices. Okay, if you sum n segments, okay, summing n segments, okay, will yield a zonotope with at most 2n. Okay, so if all the segments are, none of them, no pair is parallel to another, then you have exactly 2n, so it's lower and equal than 2n. Okay, and the zonotope will have those 2n vertices and 2n sides at most, and there will be pairs of parallel sides to the zonotope the way we got it with summing 2. Okay, and that's this summation of segments in R2. That's something, and in you know, it can be generalized to any dimension, real line, Rk, and so on. That's something that appears when you draw a sample, and every sample, after some calculations, it provides you a segment. So the chance to have collinear two segments is probability 0 if some of the appropriate variables have continuous distribution. Okay, so that's about the summing of the Minkowski sum of segments. And thank you for watching this video. and see you in the next video. Thank you.